Start. Hello everyone and welcome to Percona Live 2021. In today's session, we will learn about how Amazon Aurora supports critical MySQL workloads with a global footprint, have a strict availability requirements, and may need to tolerate region-wide outages. So we will see how Aurora global databases address those requirements. First of all, I'm Vijay Karumajj. I'm a senior specialist database solutions architect here at AWS. I specialize in MySQL database engines, including Aurora and RDS MySQL. So today's agenda is we will start with an overview of Amazon Aurora and its architecture. Then we will dive deep into Aurora global databases. We will also cover some features we have released fairly recently around write forwarding and managed plan failovers. Then we will see how to monitor Aurora global databases, and we will end the session with some of the best practices around it. So let's get started. So what is Amazon Aurora? Amazon Aurora is a database we build for the cloud. It combines the speed and availability of the commercial database engines while also keeping the simplicity and cost effectiveness of the open source database engines, which means there is no license to manage, no licensing cost. There are no additions to worry about because Amazon Aurora offers all these features out of the box. Amazon Aurora is compatible with open source database engines. You can choose either MySQL or PostgreSQL. This means the code you wrote for either of these databases will continue to work with Amazon Aurora without making any changes. And also, all of this comes with the AWS promise of simple pay-as-you-go pricing. So let's take a look at cloud native database architecture and what we have done in AWS with Amazon Aurora. First of all, in Amazon Aurora architecture, the fundamental thing is that we have separated compute from storage, which means that we can scale compute separately from storage. So we can optimize a whole lot of things along with the lines of database performance, but also durability and availability. Amazon Aurora has a purpose-built, log-structured, and distributed storage under the covers. Storage volumes get striped across hundreds of storage nodes. The bottom part of the slide represents the storage nodes in gray and purple color. As you can see, these nodes are machines with processing power and memory with locally attached high-speed NVMe SSDs. And the database process doesn't know the intricacies of the storage. So to the database, it is simply represented as a logical clustered storage volume. And if you look at it at the bottom right corner, we also continuously backup and stream the data and log records to S3 for additional durability. Also, with Amazon Aurora, storage scales automatically in 10 GB increments up to 128 terabytes maximum size. As part of the distributed storage architecture, Aurora always writes 6 copies of the data across 3 availability zones. For example, when you issue a commit or generate a log record in Aurora, the log record is sent to 6 different copies of the data in 3 availability zones. The transactions can only move forward and get committed once at least 4 out of these copies send acknowledgement back to the primary node saying that it received the data. Another fundamental part of the Aurora is we have a primary instance where you can issue both read and writes, and you can add up to 15 read replicas where you can read the data but you can't write the data. And another important point with the read replica is that read replica shares the same underlying storage and they can act as failover targets to the primary instance. And if you look at it, you can also add these read replicas in an auto scaling group where you can scale the read replicas as per your workload. We also support automatic scaling of the primary as well as read replicas using Aurora Serverless that we announced at reInvent last year. In addition to that, we also have a product called RDS Proxy, which you can use to support more connections to your database and offload a lot of connection management that the database traditionally has to handle. The proxy can also help you in an event of a failover from your primary to a read replica. It can detect failovers much quicker. What do we mean log structured and distributed storage means? So let's talk about what happens in traditional database systems. When we update, write something, the log applicator, which exists in the compute node, has to build the data pages, and then during the checkpoint, we flush those data pages to disk. But in Aurora, what happens is database instance writes redo log records to storage. Once we get, as you know, the storage spans across 3 availability zones, 2 copies in each AZ. Out of those 6 copies, at least 4 of them will send an acknowledgement back to the DB instance, then transactions will move on. Once that is happened behind the scenes, what happens is the storage materializes these data pages, and then it sends those log records and then data pages directly to Amazon S3 for the backups and then for point-in-time recovery. So let's look at the Aurora IO profile. This is an important thing to note with Aurora. On the left, we have an example of a traditional relational database, in this case MySQL, and you can see there are a lot of arrows here going from primary instance over to the secondary instance and then down to the storage on each sides. If you look at those arrows, right, we are writing log records and then binary log files for the replication, and then actual data pages, and then secondary indexes or double write buffers we are writing, and then any dictionary objects, FRM files we are writing. There are quite a lot of writes happening on the traditional MySQL systems. There was a simple benchmark run here for 30 minutes, and the MySQL machine managed to push through 780,000 transactions, so an average of little bit more than 7 IOs per transaction. If you look at the Aurora side, what's interesting is you can see there is only 2 colors used for IO. That is purple, and then there is an orange which is going towards Amazon S3. So as we discussed, all we are writing is redo log files to Aurora storage. Once we get 4 out of 6 quorum, then transactions moving on, and asynchronously we are writing the data pages. And then the same redo log file sent to the read replica just to invalidate read replica buffer cache. If there are any pages, we need to make sure we need to update them. So all we are writing is redo logs to storage subsystem. So if we look at the numbers from the Aurora side, right, because we are doing less IO, Aurora was able to support 35 times more transactions and generate 7 times less IO, which makes Aurora significantly more efficient in handling high throughput transaction workloads. If we zoom into one of the storage nodes, and again this applies to global databases, which is why I want to cover it here. If you can see, this is the code basically that runs inside each of the storage nodes. So let's see, the database instance is the primary node which sends the log records. We first put them into incoming queue, which is in the buffer, and then immediately we will send them to the hot log, which is the local SSD drive. Once we have the log record in SSD drive, we send an acknowledgement back to database instance. That is the only thing that happens synchronously. So then what happens after we persisted it, right? And in step 3, then we need to make sure that we have all the log records in sequence. But if we are missing one of the log records, the undo and redo protocols won't work during the recovery stage. So let's say, for example, we have log records 5 and 7, and we are missing number 6 log record. Then at that point, we talk to the peer storage nodes and get that number 6 log record which was missing. Once we have all the log records, then every once in a while we go and generate the data pages. Why do we generate the data pages, right? If you think about it, if a read replica comes in and asks for a page that we haven't yet generated, then we will do it on the fly. This is also why we're generating these pages, because if we are always did it on the fly, it would be too slow because it takes obviously some time to apply the log records and generate the databases. And then at step 6, we periodically stage logs and new databases versions to S3 so that we can do point-in-time recoveries, and periodically remove old versions of the databases that we don't need anymore. And at the last step, we also validate consistency of the databases that we have. Now that we have understanding of Aurora storage, let's go into Aurora Global Databases and see what we are doing there. What is Aurora Global Database? Amazon Aurora Global Database is a feature designed for globally distributed applications, allowing a single Amazon Aurora cluster to span multiple AWS regions. It uses physical replication to replicate across regions without impacting database performance. Enables fast local reads with low latency in each region, and provides disaster recovery from region-wide outages. So basically it covers two main use cases. First one is applications with worldwide footprint can use reader instances in the secondary AWS region for low latency reads. And in second, in an unlikely event of a region degradation or outage, one of the secondary regions can be promoted to read and write capabilities in less than 1 minute. Let's zoom in here a little bit into what you can do with Aurora Global Databases. On screen, what we have is Ohio as our primary. Application A is doing both reads and writes. And we have Oregon as the secondary region, where application B is doing the reads. And we have two more secondary regions, Northern Virginia and Ireland. Our storage tier are replicating from Ohio primary region to Oregon, as well as to Northern Virginia and to Ireland. Aurora Global Databases replication supports up to 5 secondary regions, so you can have total of 6 regions in your global database cluster topology, a primary and 5 secondaries. Another important point here is in each secondary region, you can have up to 16 read replicas. So across the Aurora Global Database cluster topology, you can have up to 90 read replicas. That means you can have a very large read throughput globally. Generally, you will see less than 1 second cross-region replication lag. That depends on a little bit on the region and the distances. So there is a risk of losing 1 second of data. And there is a faster recovery time we get with Aurora Global Databases. This is really important. Note that if disaster happens, making the secondary region primary generally takes less than a minute. So that's important compared to, for example, going and trying to do restore from backup, which takes more time. And another important thing is Aurora Global Databases supports very high throughput, which generally a problem with this type of configurations across the region. It's up to 200,000 writes per second with very negligible performance impact. And this is again because you can see storage tier is what does the replication, not the primary node. Let's go ahead and see how actually storage level replication works. First of all, the primary instance sends log records, as we discussed before, in parallel to the storage nodes, and now includes the replication server as if it is one of the storage nodes. And then the replication server in turn streams those log records to the replication agent in the secondary region. And replication agent sends those log records in parallel to storage nodes and read replicas in the secondary region to invalidate the buffers. And in case if the replication server does not have log records, it's kind of like a ghosted protocol for the storage node. It pulls the log records it's missing from the storage nodes, take those log records and sends it to the replication agent in the secondary region. So what about performance? As I mentioned, with global databases, we can support up to 120,000 writes per second. Here we see comparison between logical binary log replication that is configured cross-region, which you see on the left, versus the physical replication that global databases is based on the right side. In the logical replication, as the number of queries increases in a stepwise manner, the replication lag observed on the target cluster increases exponentially, which is around 10 minutes. Additionally, the number of queries per second that the tested configuration could handle at the peak around 35,000 transactions per second. If we go on the right side and look at the global databases, you see the queries per second ramps up here about 200,000 writes per second, and the replication lag you can see stay well below 1 second here. We hardly ever go over half a second in terms of lag. Again, this affects both RPO, recovery point objective, as well as the freshness of the data in the secondary side. Let's take a look at global databases write forwarding. Well, let's start with the use case. It's all about easier application development. If we look at this, bringing data closer to the users, that's what we talked about before. What about if the user needs to write? So in this case, I have readers in multiple regions, but also now apparently secondary region EU West wants to be able to write. So how do I handle this? Well, without write forwarding, the app needs to know that if it needs to write, it needs to connect to primary region, and it needs to have a way to connect there and then issue a writes. So that just increases the application complexity because you need to handle two endpoints, one for writer and one for reader. And also it increases configuring network securities and so on. So what does write forwarding give you? It enables you to simply connect to the reader and issue writes, which allows application in the secondary region to use single endpoint for reads and writes. Let's see how write forwarding works in action. So we have the same setup. Primary region is Ohio, and we have three secondary regions, Oregon, Northern Virginia, and Ireland. We have app A, which is our primary region app, and we have app B in the secondary region where it wants to do some writes to the writes in the secondary region. So after we enable write forwarding feature in the secondary region, the replica in the secondary region now can accept read and writes from the application using the same endpoint. So app B writes something in the secondary region. Aurora forwards those SQL statements along with the session context necessary to execute the statements to your primary region cluster, where we establish connection, then execute on primary region instance. Also, there is no risk of conflict because writes only happen on the primary. And then we acknowledge it, and then any results from executing these statements, including warnings and errors, are returned to the remote instance and then to the application. The entire process is transparent to the application. You only need to enable write forwarding for the cluster. To enable write forwarding feature, you have to be on MySQL 5.7, which is Aurora MySQL version 2.08.1 or later. And also you have configurable concurrent sessions and session timeouts, which will give you flexibility in number of connections you can allow from the secondary regions to do some writes. And also we have provided you three consistency levels: eventual consistency and session consistency and global consistency. In the eventual consistency mode, what happens is read queries use the current state of the secondary region's data, but it does not wait for the replication to catch up. That is the reason we get best performance for workloads that can tolerate slightly stale data. In the session consistency mode, read will wait for the replication to catch up to the most recent write issued in the same session. In practical terms, what it means is that particular session is guaranteed to see its own data, but it is not guaranteed to see changes issued by the other sessions. The global consistency mode is the strongest consistency mode. When using this mode in your application, the reads are guaranteed to see all changes that are happening at the entire global cluster up to the point when the query is started. This mode provides strongest read after write at the expense of the performance. As you increase the consistency level, your application spends more time waiting for changes to be propagated between AWS regions. you can choose the balance between fast response time and performance. Depending on the specific transaction in your application, you may or may not require read after write consistency. You may want to wait for replication to complete and make sure that you can read the previous write, or you may want to improve performance and continue with the next statement without waiting for the replication to complete. So you have flexibility on using all these consistency levels, and you can use all these consistency levels to any of the specific sessions as well. And there are few limitations when you execute statements from secondary. You cannot do DDL statements, table lock statements. You cannot do some of the load statements for permanent tables, exit transactions, and updating a permanent table using data from temporary tables, etc. Let's look into some of the benefits of the write forwarding. So first, it's a managed solution. Writes issued at remote clusters are transparently forwarded to the primary cluster using secure cross-region communication channels. No replication conflicts because all the writes are applied by the primary cluster. So we have only one writer in the primary. So we are not writing anything in the secondary region. All we are doing is simply forwarding those writes to the primary cluster. And third one is, it's pretty simple. You can issue writes to the remote cluster followed by reads that will observe the previous writes. And also you have flexibility in choosing the several read consistency levels to balance consistency and performance. Okay, finally I want to cover Global Databases Managed Plan Failover. This feature is released February of this year. So let's look at it, some of the use cases. Aurora Global Databases Managed Plan Failover makes it very easy to test your disaster recovery drills. And the use case is for performance reasons or some of the compliance reasons. If you have a distributed read use case, you may want to move your primary to a secondary region. For example, I have seen some customers moving their primary region to secondary region quarterly. If you have one of those requirements, and if you have to move your primary region to secondary region, you can do it pretty easily. Aurora Managed Plan Failover still maintains your replication topology even when you move your Aurora cluster from region A to region B. And also it maintains RPO with 0 seconds. After you fail over your cluster from region A to region B, you simply need to repoint your application to newly promoted primary and you should be good. Let's see how Managed Plan Failover work in action. Well, I have my setup again with Ohio, Northern Virginia and Ireland, and the application is running against the Ohio in this case. Because of some reason, probably the most common thing here is that you want to test out your disaster recovery solution. So basically this is a disaster recovery drill. You're moving your application over to the Northern Virginia to verify that your disaster recovery plan works and is fast enough for your business. So we click the promote Northern Virginia to be new primary region. Then Ohio writes will be stopped. So we make sure that we drain Ohio. We never lose any data. This is totally managed for you. And then the secondary region both catches up to make sure they got all the writes that happened in Ohio. Then Northern Virginia becomes the new primary. Now it can accept the write workload. And then you need to point your application to Northern Virginia cluster endpoint and you're good to go. So everything here is managed for you. Outside of your application needs to be repointed to Northern Virginia's cluster endpoint for it writes. From the monitoring side, Amazon Aurora delivered as a managed service, so it has built-in monitoring and health checks to operate the service. It also provides tools to monitor database operations and performance metrics like CloudWatch, enhanced monitoring, performance insights, and RDS events. So from your side, you have to set the workload, appropriate thresholds, and configure alarm and notify based on monitoring metrics. You also have capabilities to enable and configure desired database logs like CloudWatch logs, general logs, and audit logs. And I want to call out a few specific monitoring questions I normally get when I talk to customers. Why my performance insight metrics are missing after a region failover, and how do I monitor replication lag, how much data transferred between the regions, etc. So for performance insights, when you add new secondary AWS region to an Aurora global cluster that's already using performance insights, make sure that you enable performance insights in the newly created cluster, because it doesn't inherit the performance insights setting from the existing global databases. And some of the CloudWatch metrics to monitor: Aurora Global DB replication lag. It will show you the replication lag between primary and secondary. And Aurora Global DB replicated write IO, the number of write IOs replicated to the secondary region. From the billing side, you can monitor Aurora Global DB data transfer bytes, the amount of redo logs transferred between the regions. You can see volume read IOPS and volume write IOPS, the number of build, read, and write operations happened from the billing point of view. Let's look at best practices for multi-region global clusters. Set up a network topology ahead of time, things like VPC, subnet groups, and configure network security groups, etc. Set up authentication configurations like IAM roles and secrets manager integration for database and application logins ahead of time. Decide on encryption strategy and make sure you have appropriate encryption keys ahead of time, like customer managed keys, or decide with default KMS. And same thing goes with client-side encryption certifications. Make sure you have bundles and region-specific keys in the secondary region as well. If you are using custom DB parameter groups on your clusters, ensure consistency in DB parameter groups exists on both sides. During the DB upgrades, make sure upgrade the secondary regions first. As we discussed, choose appropriate consistency model to balance between fast response time and performance for global DB write forwarding clusters, and often test your disaster recovery drills using managed plan failovers. That's all I have today. Quick summary of our today's session is: we learned that Aurora Global Databases allows you to create globally distributed applications that can serve local reads in remote regions. You can maintain a disaster recovery solution with minimal RPO and RTO. With write forwarding, we have seen you can now enable your global applications to perform writes in secondary regions. Also, we discussed how easily you can do disaster recovery drills using managed plan failovers. Thank you for taking your time and attending today's session on Aurora Global Databases. Enjoy the rest of your sessions at Percona Live. Reach me for questions at the email address on the screen. Have a good rest of the day. Thank you.